Hey everybody, today we're working on Unit 17, Entropy and Gibbs free energy. These are the last two of the thermodynamic quantities that we're learning in this last unit on thermodynamics. Um, Entropy, we've talked about a little bit in class already. It's a bit about randomness is one way to think about it, and Gibbs free energy is really used to see if a reaction will happen spontaneously or not. We're going to go over these today, a couple practice problems. Let's get started. Okay, starting here with some definitions, we have the first law of thermodynamics, which says energy cannot be created or destroyed. We also call this the law of conservation of energy. This law can only account for energy's presence. It does not account for why a particular process occurs in a given direction. That's what we're going to be talking about today. Gibbs free energy and entropy help explain that. Okay, so talking a little bit back, over here on the right, we have like a energy diagram that shows the pathway of a reaction. So starting over here on the left side, my reactants. On the y-axis is my energy. So they start off with energy about this relatively high. Okay, this up here it says domain of thermodynamics. That's kind of what we're talking about today, the initial conditions of the reactants and products. Now, this lighter blue, greenish color in the middle says domain of kinetics. This is the reaction pathway, how the reaction happens. The energy goes crazy during a reaction. But today we're just talking about our initial and final states. All the thermodynamic functions or quantities are what we call state functions, meaning you don't care about this middle, how the reaction happens. We learned that with kinetics. We care about what we start with, what we end with. Okay? The rate of a reaction depends on the pathway. Thermodynamic tells us whether a reaction is spontaneous based only on the reactants and products. So this isn't something to be asked about, but just kind of thinking about why we're learning this. We're learning this to kind of look at just our initial reactants and our products, and we can predict things about the reaction looking at that, ignoring all this complicated middle region. A spontaneous process is one that occurs without outside intervention. It happens spontaneously. Thermodynamics lets us predict whether a process will occur, but gives no information about the time required for the process. That's what kinetics tells us, how long the reaction is going to take, if it's first or second order. So we can look at these things kind of hand in hand to learn the most about our reaction possible. All right, our first quantity today is entropy. Sounds very similar to enthalpy. I'll accidentally say their names for each other all the time. Terrible decision to name it this. Its letter is S, which also doesn't make a lot of sense, but let's go with it. The driving force for a spontaneous process is an increase in the entropy of the universe. Okay, now we're going to talk about entropy in a couple different ways, and it's kind of confusing. It's like I like to say there's like a high school level explanation, which I'm going to give you, and then a college level explanation, and since we're in AP Chem, we'll talk about that. Then there's like some other really advanced physics explanations that I don't understand that we're not going to talk about, which makes it a really hard topic to teach. So, like lots of things with chemistry, there's multiple definitions depending on how advanced you want to go. What we're going to start with is a measure of molecular randomness or disorder. Okay. Like I said, entropy is the measure of disorder or randomness of a system. A more technical definition describes entropy as the unavailability of a system to convert its thermal energy into mechanical energy. And I'm going to give you an example to kind of talk about a little bit more what I mean by that in just a second. A positive S, a positive entropy, means entropy is going up. You can think of that as things getting more random in some way. A negative S means entropy is going down. Things are getting more organized somehow. Usually you have to put in work to organize your system. Talking about entropy, okay? It feels weird that something like entropy is an actual tangible energy quantity because it's like randomness. Why does this matter? Um, it's just how random is something. But its value is real and can be thought of like how easy it is for my system to accomplish its goal, to accomplish the reaction I want to do. So here's my example. If I want to eat 20 red Skittles and I have a bag of mixed Skittles, I have to like dig through and find 20 red ones. I'm pushing a lot of the other ones I don't want to the side. I am putting in physically extra work. But if I already went ahead and organized them into like sections into different colored candies, then it's a lot easier to accomplish my work. Okay? The system where I went ahead and organized ahead of time has a lower entropy. The system is not trying to stop me from doing work. But the system where all the M&M or all the Skittles are all over the place, I have to actually put in more work to make the reaction of me eating 20 Skittles happen. So entropy is basically a measure of how much harder the system will make it to do something. Very random things have a high entropy because everything is everywhere. It's hard to accomplish your goal when things aren't nice and organized. You have to put in more effort. Okay? Organized Skittles. They have a relatively low entropy. I could pick 6 green and 2 oranges really, really fast. I needed that for my reaction. And then disorganized, I could go through and find that, like, no, it's not too much extra work, but it would take extra work to dig through and find the exact set of colors you're looking for. Okay? So which picture of Skittles has a higher entropy and why? Okay. Higher entropy would be the second one here. It's disorganized. Everything is everywhere. It's harder to do work. The unavailability of the system to do work is higher. Okay. Usually the context we need entropy for is for states of matter. Think about the molecular structure of solids, liquids, and gases. Which would you expect to have the highest entropy and which would be the lowest? Okay. So if we're going with the randomness versus organized, solids, nothing's moving. Everything is in a nice, neat pattern, attracted to each other by intermolecular forces. It's very easy to find where all your stuff is. So solids have a very low entropy because they're very organized. Think about gases. You can't contain gases. The molecules move independently around their container. It's random where they are. Okay? So that has a very high entropy. Liquids are in the middle. Gases have the highest entropy because their molecules are the most disorganized. Solids have a low entropy because they are boring and a nice, neat pattern, or they are organized, you could say, not random. Okay, so here we have a couple different examples, some conceptual, some with reactions. Determine if the entropy increases or decreases in the following scenarios. First, a popsicle melts on a warm summer day. So, starting with a solid popsicle, goes to a liquid. Solid to liquid. Liquids have more entropy than solids, so that causes the entropy to increase. Second, I take a shuffled deck of cards. Okay, so if I think about the shuffled deck of cards, everything is completely random. And I sort them by suit. Okay, so I'm sorting them, I'm organizing them, kind of like with my Skittles. I'm causing the system to get more organized, therefore entropy is going down. Okay, now here with some reactions. More like what you could see on questions. These questions are very popular, like the multiple choice section. So I have bromine liquid turns into bromine gas and heat. Liquid, lower entropy, gases, higher entropy. Entropy is increasing during this reaction. Second reaction here, I have this large solid. It splits into some solids, liquids, and gases. Well, solids have the lowest entropy, so these liquids and gases have higher entropy total. So this also is an increase in entropy. The last one can be a bit tricky here, so we have to be careful. On the left side of my reaction, I have H2 gas and O2 gas turns into water vapor, H2O gas. So what I need to do when I have gases on both sides of my reaction is figure out how many total moles of gas I have. So I'm just adding together the coefficients of all my gases. I have 2 over here and 1 over here. So on the left side, I have 3 moles of gas. On the right side, I just have 2. So when this reaction happens, my number of moles of gas is going down, which means my entropy is also going down. Okay? So those are questions you could expect to see. More likely these reactions, but they could ask you a question sort of like one of these two as well. Okay. Now we're going to talk about the second law of thermodynamics, which involves entropy. In any spontaneous process, remember spontaneous happens by itself, there's always an increase in entropy of the universe. Another way to phrase that is the entropy of the universe is increasing. Things are continuing to get more and more randomized. The total energy of the universe is constant, but the entropy is always increasing. So the entropy of the universe equals the entropy of a system plus the entropy of the surroundings. but in a spontaneous process, the entropy of the universe goes up. This will have some context we'll get to later. This equation can be used to determine whether a process is spontaneous. If the entropy of the universe is positive, the process is spontaneous in the direction written. Okay, so this would basically be like, I give you a reaction, and then off to the side, I'm telling you this information. If the entropy of the universe is positive, that means the reaction is spontaneous. If the entropy of the universe is negative, the process is spontaneous, but like in the opposite direction. So the current direction it's written is not spontaneous, but if you flip it around, it would be. And if the entropy of the universe doesn't change, the process has no tendency to occur, and the system is at equilibrium. So if the entropy of the universe doesn't change, we have a reaction at equilibrium. Okay, 1 second. This is the first way we're going to determine spontaneity. Now this one's really just this kind of definition you need to know. When we get to Gibbs free energy, that's our main way to predict if something's spontaneous or not. But this is just kind of a backup way. Or I guess, yeah, whatever. All right. Next section, the effect of temperature on spontaneity. How does the temperature of something affect how a reaction occurs? Entropy changes in the surroundings are primarily determined by heat flow. Exothermic reactions will increase the entropy of surroundings. That means the entropy of the surroundings is positive. Okay. Entropy and enthalpy are so hard to say separate. Okay. Endothermic reactions decrease the entropy of the surroundings. Okay. So another way to say that, entropy of the surroundings is negative. Okay. So remember, an exothermic reaction gives off heat. That means the entropy of the surroundings goes up. In an endothermic reaction, it kind of absorbs heat. Okay, so the surrounding entropy has to go down. At lower temperatures, the transfer of a given quantity of energy as heat produces a much greater percent change in the entropy of surroundings at low temperature. This property is represented by this equation. You can write this down. It's not something we're really going to have to solve. This is all just to help us understand this conceptual idea. Okay. Basically, this is to help us understand that entropy relies on temperature, which we'll get to later when we talk about our next equation. Now, here's the enthalpy of the surroundings. The sign of the enthalpy of the surroundings depends on the direction of the heat flow. Right? So whichever way the heat is traveling, the entropy will increase or decrease in the same direction. The magnitude of the entropy of the surroundings depends on temperature, which we need for this equation. Thus far, we've used the entropy of the universe to predict the spontaneity of a process. That's a way you can do it. It's kind of archaic. This reaction below is the one we're going to use to predict if something is spontaneous or not. It takes into consideration all the things like how the entropy relates to temperature and stuff. And the overall idea is called free energy, also called Gibbs free energy, like Gibbs, Gibbs. Okay, that's why it has a G as its symbol, which helps it make more sense. Free energy is a thermodynamic function that's useful for dealing with temperature dependence on spontaneity. The free energy flow of a reaction lets us figure out if this reaction will happen at this temperature or not. Okay? To calculate free energy, we use this equation below, which we're also using in class on our worksheet. This is a very popular equation to solve for thermodynamics in general, because it's actually going to include all three of the thermodynamic quantities in one equation. I have G, which is Gibbs free energy, equals H, which is my enthalpy, okay, minus temperature. Temperature is always going to be in Kelvin for these problems. If it was in Celsius, the negative sign could really throw things off. So we leave it in Kelvin always. S is entropy. So if we take the entropy change minus temperature times entropy, hopefully I said that right, that gives you Gibbs free energy. If you want to know the change in free energy, you have this exact same equation. We just add these little triangles that mean change. We'll talk about when to use these two different equations in our examples in just a bit. All right. Through substitution in algebra, the equation can be written as this. Okay. But this only works at constant temperature and pressure. This equation is important because it means that a process carried out at constant temperature and pressure will be spontaneous if delta G is negative. In other words, a process at constant temperature and pressure is spontaneous in the direction in which the free energy decreases. Let's see if I have this written. Okay. What this means, if G is negative, the reaction is spontaneous. If G is positive, the reaction is not spontaneous. That's mainly what that's useful for. That's translating that long paragraph. Okay. All right. So here we go. Here is their AP exam's favorite chart. Okay. And it's really hard to think about these ideas. This chart shows the relationship between spontaneity and the three thermodynamic quantities. Okay. The main thing that affects if something is spontaneous is the value of G. The value of G overall will tell you if something's spontaneous or not. So if it's a negative, it's a spontaneous reaction. If it's positive, it's a not spontaneous reaction. But we don't always know if G is going to be positive or negative without plugging in the numbers first. And because of how these values go and the negative signs, it can get kind of confusing to think about. But to try this, the easiest way is just to plug in an example. So what I mean by that, we have the value of delta H. If it's a negative enthalpy, which means it's an exothermic reaction, and if S is positive, meaning entropy increases, that means that reaction is always spontaneous. So if you have a negative number for H and a positive number for S, your G will always be negative because of how the signs work in the reaction. So this reaction will always be spontaneous. Okay, now for example where you have the second column here, if you have a positive entropy, positive enthalpy, that means you have an endothermic reaction. And if at the same time you have a negative entropy, meaning entropy decreases, then that reaction is always going to give you a positive G and will always be not spontaneous. Okay. Now, the other two situations that can happen are if both values are negative, meaning it's exothermic but entropy goes down, or if both values are positive, meaning it's endothermic but entropy goes up. For those, you have to plug in your values to figure out if delta G will be positive or negative. Okay. For this third column here, third row here, negative, negative, will be spontaneous at low temperatures. Positive, positive will be spontaneous at high temperatures. So T is temperature, and it's going to affect if it's positive or negative because you multiply it by the entropy. Okay. So at high temperatures, entropy becomes the more important quantity because this is going to be multiplied by a really large number. But at low temperatures, H is going to be the more important quantity. So its sign is going to affect the value. Okay. So it's kind of weird to think about. We're going to do some examples of these as we go in class, where I'm just going to give you a value of H and a value of S, or tell you the sign of H and the sign of S. And we're going to use that to predict when the reaction is spontaneous or not. This is a very common question. My advice for solving this sort of question, especially if you get some of the hard ones like these two at the bottom, just make up numbers and plug them into the equation and see what G turns out to be. So this is negative. Just think of a number that makes it negative, negative 10. This is negative, throw in a negative 10. And then for this reaction, where you don't know for sure which way it's going to be, make the temperature really, really high one time, so make it like 1,000,000. And then make it really, really low, like 0.001. And then see how it affects the change in G at high and low temperatures. Plugging and chugging and substituting in, trying an example is the best way to figure this out, especially if your brain's a little foggy like mine is when I try to teach this in class. At what temperature is the reaction here spontaneous? If enthalpy, is 44 kilojoules per mole, and entropy is 818 joules per Kelvin mole. All right, so let's use our new reaction we learned. This is what we need. Delta G equals delta H minus T delta S4. Okay. So I want to know what temperature is this reaction spontaneous? Okay. So let's think about what that means. Spontaneity depends on the sign of G. So if we think about it, at 0, the reaction would just be on the cusp of reacting, but not quite reacting. But anything above 0 would be a positive number. That means it would be non-spontaneous. Anything below 0 is a negative number. That means it would be spontaneous. Okay, so what we're going to do is set delta G to 0. And figure out what temperature would be once we plug everything else in for delta G equals 0. The answer we get for this temperature will be the exact temperature that is like the cutoff. Anything above this temperature is non-spontaneous. Anything below it is spontaneous. That's kind of our idea here. The main thing to get from this, let's set delta G to 0, plug in everything else, and see what we get. So my enthalpy, H, is 44 kilojoules per mole. Try to focus this a bit better. Okay. Minus temperature is what we're going to solve for. And entropy. Entropy is 118 joules per Kelvin. This enthalpy is kilojoules, entropy is joules. So we can't add them together. So I'm going to take this joules, this entropy, and turn it into kilojoules by just dividing by 1,000. 118 divided by 1,000 is just 0.118. So I plug that in for T, or for S, excuse me. And now we just have a reaction to solve with this one variable. Okay, so to solve, I'm going to add this over to the left side to cancel it out. And I get 0.118 times T equals 44. Now divide each side by that. 44 divided by 0.118 is like 373. Remember, the units for this will always be Kelvin, not Celsius. Okay, that is the that's the borderline temperature. Okay, so what we can do now to test which direction okay, so this is the answer to the question, so I should say. But let's plug in to see what if we have something at 374 Kelvin. If I slightly increase the temperature above this, how is the reaction going to fare? So now I'm just going to plug in everything back in just to test it. My number here is still for enthalpy is 44 minus 374 times my entropy, and just see what delta G turns out to be when you do that. So I have 374 times 0.118 is 44.132. So I have 44 minus that. This would be a negative 0.132. At 347, sorry, that's 374. At 374, the reaction is spontaneous because this is negative. Okay, so that kind of proves our answer. We checked our work by plugging in our stuff back into the question. All right, so far we've only applied the second law of thermodynamics, the whole entropy of the universe thing, to physical processes such as changes of state. Chemistry, however, is about chemical reactions, and therefore we're now going to try to apply it to full chemical reactions. All of these are going to occur at constant temperature and pressure, otherwise we won't be able to calculate the entropy correctly. Okay. A lot of weird definitions with energy and heat flow and stuff like that. Entropy changes in the surroundings are determined by the heat flow that occurs as the reaction takes place, mainly being exothermic or endothermic. Entropy, like the surroundings, remember, are the environment around the reaction. So an exothermic is going to release heat, so the entropy will go up. Endothermic is going to absorb heat, so the entropy around it goes down. Now, entropy changes in the system itself, the reactants and products, are determined by positional entropy. Now, this is where the entropy we talked about before, like the Skittles, is going to come into play. Reactions involving gaseous molecules. The change in positional entropy is dominated by the relative number of molecules of gas, reactants, and products. Take this reaction of ammonia into account. I have on the left side my reactants. I have 4 reactant molecules. I have 3 H's, 1 N, so 4 total. Produces only 2 product molecules. This lowers the number of independent units in the system, leading to less positional disorder. It's getting more organized because I have less gases, entropy going down. So let's predict the sign of the change in entropy for the thermal decomposition of a solid calcium carbonate. Okay, I have on the left side some CaCO3 becoming CaO and CO2. Well, I see CO2 on the right is my only gas, so when this reaction goes, it produces a new gas. Entropy goes up. A perfect crystal represents the lowest possible entropy. The entropy of a perfect crystal at 0 Kelvin, at absolute zero, is exactly 0. So that's the only way to have a 0 entropy thing. It's like a perfect crystal. Think about like a perfectly shaped diamond with no impurities at 0 Kelvin. Everything else is going to have a positive entropy. One can calculate the entropy value for a substance at a particular temperature by knowing the temperature dependence of entropy. This reaction might look familiar. This is the same reaction that we used for enthalpy. There's also one for Gibbs free energy. The change in entropy of a reaction is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. Entropy is an extensive property, meaning a function of the number of moles. Generally, the more complex the molecule, the higher the standard entropy value. Makes sense. If it's complex, say it's a really large molecule, you need to react with a specific part. It's going to be harder to do that because now you have to like orient the molecule the right way and stuff like that. So you can look at a data table for a reaction like this and calculate its entropy just like we did with enthalpy. So let's do that now. I want to calculate the change in entropy at 25 Celsius. Now the temperature doesn't matter. It's just that's telling us that the temperature is not changing. We can use this data table basically. We're not multiplying by temperature specifically. Okay. For the reaction below. So I have my reaction. I have some NiS, some nickel sulfide, and 3 oxygen molecules on the left, producing 2 sulfur dioxide molecules and 2 nickel oxide. Okay. So before I do my math here, I want to predict, do I think the entropy is going to go up or down? Well, on the left side of my reaction, I'm looking for gases. Those dominate the entropy. Okay. So I have 3 moles of gas on the left side. I have only 2 on the right. So most likely my entropy will go down, meaning my answer here should be negative. And we'll check our answer as we go to see if that's true. Now, you can get some really close situations where it technically wouldn't be, but that's our best way to predict. Let's write our reaction, and I'm going to simplify it based on how it's written there. I'm just going to write delta S. Now there's technically a little circle here, which means it occurs at standard temperature and pressure. You can include that if you want, if you like how it looks. You don't have to. You can write the whole word below here too and stuff like that, but that's what that little thing means. It's just at standard temperature and pressure. That's not changing. Okay, so I'm going to have the sum of the entropy of the products minus the sum of the entropy of the reactants. Okay, so I like to show my work very carefully here because the negative signs in some of these can mess it up. Now with entropy, all the values are positive, so it makes it a little easier, but just to be careful. So my products first. My first one is some SO2. So I have 2 times, let me find the value for that. 2 times SO2 is 248. I'm taking the sum, so I'm going to add here, plus my 2 NiO, which is the 38. Make sure again to multiply it by 2. That's what my product side looks like. I just take the number of moles in the reaction, so they both have a 2, so I'm multiplying their numbers by 2. And then I just find their number on the chart. Okay, now my reactants, first I have my 2 NiS, which got cut off this chart, but the number is just 53. So I'm going to write that there. Plus 3 times oxygen is 205. Now, if you look at the table here, you'll notice that the gases have a much higher entropy number, which makes sense based on what we've been saying. The solids are much lower than the gases. Okay, so here's my reaction. Now I'm just going to do my math to solve. So I'm just going to add up everything on that left side together first. 2 times 248, 496, plus 2 times 38 is 76. Keep it in brackets so it looks nice. On the right side, I have 2 times 53, which is 106, plus 3 times 205, which is 615. Now add everything up together. 496 plus 76, 572, minus 106 plus 615, 721. Okay, subtract that, I get negative 149 kilojoule. No, this one's probably just, this one's in joules. Yeah, joules is your answer. So it is negative like we predicted, which makes sense because we are decreasing the entropy by making less gases. Okay. For chemical reactions, we're often interested in the standard free energy change. So I said standard, that's what the little circle means. It just means temperature and pressure aren't changing. Free energy change is the G. The change in free energy that will occur if the reactants in their standard states are converted to the products in their standard states. Standard free energy cannot be directly measured, but it can be calculated from other measured quantities. The general trend is the more negative the value of delta G, the farther to the right the reaction will proceed in order to achieve equilibrium. So the more negative delta G, the more the reaction is going to be product favored at equilibrium. There are several ways to calculate delta G. This first method is the one we're going to use the most, and it's that reaction we learned before. We added on the little circles. Doesn't matter, we do the math exactly the same. It just means at constant temperature. So here's our next example. Consider this reaction. We have SO2, 2 SO2s plus O2 gives you 2 SO3s. So I'm looking at it immediately. If we're doing an entropy problem here, I would guess that the entropy would go down. But we're not. It says calculate delta H and delta S and delta G. So we're trying to calculate all three of those using the following data. So looking here, it gives us information about H and S. Okay. Now, when you have one of these data tables, that's when you're going to use that products minus reactants, sum of the products minus sum of the reactants. That's what this information here in this table is for. So we can do that and find H. We can do that and find S. How do we find G? Well, there's no G values in the table here, but G is related to H and S. If we know the temperature, which we do, we can plug in that, and we can just solve for delta G using this reaction. So that's what we're going to do here. So I'm going to write down my couple of reactions I need. So my ultimate goal is to solve delta G, delta H, and delta S. This one's going to be the trick, though. Okay. Draw little circles, whatever. Okay. To find delta G, I need these two anyways. Let's talk about how to find H and S. Well, we can just do the sum of the H of the products minus the sum of the H of the reactants, using the information provided to us in that data table. So let's do that first. All right. To the data table. There we go. I'm just going to look at the numbers here. All right. So my reaction, my products, I only have one product this time. I have my 2 SO3s. SO3's number there, we're going to do 2 times negative 396. Okay. Minus my reactants. I have 2 reactants. The first one is my 2 times SO2 is negative 297 plus my second reactant is O2. Now remember, okay. All right, so we're going to solve this one. Be very careful of your signs, negative and positive signs, stuff like that. All right, so I have here 2 times negative 396 is negative 792. I keep it in brackets just to help me keep my signs in the right spots. Then over here, I have this plus 0, which is great, but I have 2 times negative 297 is negative 594. Plus 0 goes away. So now I'm going to add these together. The negative minus a negative. So it's really just plus this number, right? So it would be negative 792 plus 594 is a negative 198. If I look back, I know it's in kilojoules because if I look back at my data table, it was given to me in kilojoules. All right, now we're going to repeat the same thing with S using the other information in this table. So I'm going to write a new reaction for delta S. It is the sum of the S of the products minus the sum of the S of the reactants. So my product, I only have one again, put it there, minus my reactants. So my product, 2 times, it's SO3, be careful with the number, that one's 257. Minus my reactants. So I have 2 SO2s, so I'm going to do 2 times 248 plus 1, so I have 1 O2, and the number there is 205. I know it's cut off. Now I'm going to solve this. Entropy is always a little nicer because all the numbers are positives. Makes the math a little easier. But let's solve that. Let's take our 2 times 257. 514 minus. Okay, over here I have 2 times 248. 496 plus 1 times 205 is just 205. 514 minus this equals 701. 514 minus 701. This one's also negative. Now, entropy usually is given to you in joules. If we check that data table, it's given to us in joules. So we need to be careful about that. Those are our first two answers. We're looking for delta H. We're looking for delta S. Okay, but now we need to find delta G. So we're just going to plug our answers into this equation. We know the temperature it gave us was 25 degrees Celsius. I'm just going to make sure to bump that into Kelvin. So I'm going to add 273 to get 298 Kelvin. Now let's plug everything into here. Negative 198 kilojoules minus temperature is 298. Entropy, remember, I need to make sure I put it in kilojoules. So I'm going to divide it by 1,000. And I get points negative 187. So a lot of work to do for this problem, but relatively easy. Just know like a couple of different steps you have to all put together without making any mistakes. So just do it like perfectly, okay? All right. Negative 198. It's gonna be minus 298 times negative 0.187. That's going to equal minus negative 55.726, which is really 198, negative 198 plus 55.726 is negative 142. kilojoules. Minor correction, delta S is in joules, but is actually technically in joules per Kelvin. That's why when you multiply it by temperature here, Kelvin, joules per Kelvin, the K's cancel. So it kind of works itself out. But yeah, technically entropy, when you're doing the standard entropy, should be per Kelvin. Doesn't really matter. Okay, that's our answer. My reaction is spontaneous. Okay. You could see though, if you increase this temperature even more, you ended up adding this number. So there's be a threshold if this was like 10,000 degrees where this reaction would not be spontaneous because it would end up being positive. Okay, there's also one other way to calculate delta G actually there's two other ways. This one is a Hess's law type problem. Remember, Hess's law is when you add multiple reactions together and you add all we did it with enthalpy before, but you can also do it with entropy and with Gibbs free energy. Use the equations below to find delta G for carbon in diamond form into carbon graphite form. All right, so I have my reactions here. C makes diamonds plus O2 gives you CO2. Here's my Gibbs free energy for that reaction. And then I can make graphite plus O2 gives you CO2. Now, if I want to find this reaction, I need to get graphite on the other side. Oh, okay, I cut off the work. Graphite on the other side, so I'm going to flip this bottom reaction. That turns the delta G positive. So you're just going to have the same sign, just flipped. So it'd be a positive 394. Okay, and then when you flip that bottom reaction, everything's going to cancel out except for the diamond and the graphite. Then you would add together your two Gibbs free energies here. Negative 397 plus positive 394 equals negative 3. So that's a way you could find, just like we did with enthalpy. I'm not going to go through the whole example, but that's how you could figure out the delta G of like one final reaction from several pieces. The third and final way to calculate delta G is, like I mentioned before, this reaction here at the bottom. Looks exactly like the reactions we did with entropy and enthalpy just now, but it's with Gibbs free energy instead. The standard free energy of formation is the change in free energy that accompanies the formation of 1 mole of that substance from its constituent elements, with all reactants and products in their standard states. The delta G of formation of an element in its standard state is 0. Okay, so the standard state of an element, meaning like just one of them by itself, or if it's one of the 7 diatomic molecules, having 2 of them, it will be 0, just like with enthalpy. So the only time a free element isn't 0 is for entropy. Yes. So here is our last slide here. We have one more example to do. Methanol is a high-octane fuel used in high-performance racing engines. Calculate delta G for the reaction below, given the following free energies of formation. This would be exactly like those examples we just did. You can find delta G values for formation in your in like a reference table as well. Okay, so for my reaction here, I'm going to do the same reaction. Delta G equals the sum of the G of the products minus the sum of the G of the reactants. Just going to plug all my numbers in, just exactly the same as before, using the data table, and we'll get our answer. Okay, so my reactants. First one is CO2. I have 2 of them, so I'll do 2 times negative 394. Plus, my second product is H2O gas, which is the one that's cut off on here. It is negative 229. So it's 4 times negative 229. Minus my reactants. I have 2 of my methanols. So that's the negative 163 plus 3 O2s, just 3 times 0. Right. Set up just like all the other quantities are set up. Now we just solve. That way that light doesn't glare too bad. There we go. That'll do. Okay, so over here I have 2 times negative 394, negative 788, plus 4 times negative 229. Okay. Minus 2 times negative 163. The easiest place to go wrong in these problems is messing up, putting into your calculator and messing up a sign. So just be careful when you do it. Hope I'm not making any mistakes as I'm saying that. Adding up the left here, that gives me negative 1704 minus negative 326 minus negative 326 gives me a negative 1378 kilojoules as my answer. Okay, so today we talked about entropy, what that means. We talked about a couple of ways to calculate it, including the reaction, the change, the sum of the products minus the sum of the reactants. But more importantly, we actually talked about when entropy goes up or down during a reaction or during a situation. Then we talked about Gibbs free energy. Gibbs free energy is used for determining if something's spontaneous or not. Okay? Negative G means it's spontaneous. Positive G means it's not spontaneous. We talked about 3 different ways, actually. Glazed over one of them, but there's 3 different ways to calculate Gibbs free energy. One is using the problem like in this example here. Number 2 is doing like a Hess's law type problem where you add multiple of them together to make one overall reaction you want to learn about. And the third is using that delta G equals delta H minus T delta S formula. Okay? That does it for the thermodynamic quantities and basically for the end of thermodynamics. We have one more chapter to go with this unit and this year, but it's actually slightly different. It's all about electricity and electrochemistry. So this is basically what you need to know for thermodynamics, okay? All right, thank you for watching. Have a great day.